let's start. Today I want to go through a circuit design and probably the schematic design of a buck converter. Let's say the universal one. I chose the Texas Instruments LM61440. It's pin compatible with the automotive variant and with the more higher voltage variant. Our converter is up to 36 volt at the input and 4 amps output current. The output current is limited by the internal FETs because this buck converter is synchronous. It means that there is a high side switch and a low side switch. Both FETs have some limits. So we have to consider this. And the advantage of the Texas Instruments documentation is that there is always application implementation section. So we will go through it from zero to the finished schematic. I think today we will finish schematics. Maybe we can go to the component layout. I don't know. I will give it an hour to the job and we will see how it goes. So let's start. So I will make a split screen with the KiCad schematic and the browser. In the browser there will be the data sheet. Let's say this size, and on the right side there will be schematic, but I will not start with schematic. I will start with the circuit design. It means I will make some notes. Yeah, the issue is that the text in the text field is rather small, but I will regularly save it with the higher text size, so you will see the previous text on the schematic. I think it will work. So let's go to the application and implementation section, and in the meantime I will write here the input parameters of our buck. So we have a buck with input voltage up to 36, nominal, let's say 20, not 12, output V out 3.3, 4 amps, switching frequency will be calculated or set. We have input capacitance, we have output capacitance, we have inductance of the output filter, we have feedback resistors on the upper side, we have feedback resistor FB bottom side, we have bootstrap capacitor C boot. We have when looking at the schematic on the left side, you will have the full picture of what I'm talking about. Yeah, and there are filtering capacitors and series resistor, like the feedback compensation. It's not so important for us right now, but yeah, in the text there will be explanation of how and what values we most likely will use. So we have these input values. Yeah, I will save it in a bigger font, bold. Okay, so I think we will see everything, and I will place the calculated numbers or some formulas if needed. So this is how the typical application circuit looks like. It's based on the minimal circuit. Let's say there is the bootstrap capacitor, output filter LC, there is the feedback resistor divider with the filter, not filter, it's a feedback compensation. There is a power good resistor, not important here. There is, because the switcher is has the topology with dual power entry ports, so there are two power entry ports at the each side of the IC or the package. So we will need two input capacitors on each side, at least two, maybe more, probably more. We have output capacitance, yeah, part of the filter. We have VCC capacitor and RT resistor setting the switching frequency, and there is the enable resistor. Yeah, so let's start with the procedure here. So I will go through each paragraph with formulas, and when there are some important information in the tables, I will make some notes. So here are typical external component values. Yeah, there are two switching frequencies, 2.1 MHz and 400 kHz. We will decide about our switching frequency in a minute. So take these values as example only. So for instance, for 3.3 volt, which is our output voltage, the recommendation for 2.1 MHz is 1.4 microhenry with 322 microfarad at the output. The feedback resistors are independent on switching frequency, are independent on anything else. You can see that for 3.3 there is 100 kilo ohm, the top or the upper resistor of the divider, and the bottom one is 43.2 kilo ohms, so we will use 43. I think we can start with this because these values are already suitable to our design. We don't need to reinvent the wheel. Yes, if you want to choose another, or yeah, basically a different output voltage, you need to calculate your own feedback divider. It's very simple, only you need to know the feedback voltage. So in the data sheet, it's very important information, a very important parameter. So typically it's the VFB or something like this. So let's see, here is power supply and current. History is no. So let's start looking for 𝗶𝗶, like FB. FB. Here, feedback. No, this is the initial reference voltage accuracy. Adjustable versions only. Feedback is 1 volt. So this is the feedback voltage, 1 volt. So if you want to calculate your own voltage divider, you have basically two unknowns, the top feedback resistor and the bottom one. You know the output voltage and you know the output, yeah, the top voltage, like the supply voltage of the voltage divider, and you know the output voltage of the divider. Let's say you choose 100 kilohertz to be the top one, the upper one, so you need to calculate the bottom one. And the formula is very simple. So let's say V out of the divider is R bottom times V supply divided by sum of R bottom plus R top. So if you want, let's say 4.2 volts, and your unknown is R bottom, so keep it R bot. Power supply is no, yeah, you need, I made a mistake. The output voltage of the divider is 1 volt. This is the feedback voltage. Supply is the output voltage of the converter, 4.2, divided by the sum of bottom plus top. We said that we chose the 100 kilo ohm as a top resistor. So there is simple calculation. I don't want to continue, but you know that the voltage will be probably like 36 kilo ohms or something. I have a helper here to save my energy. I have a spreadsheet I'm using quite frequently, and here it is. 100 kilohertz is the top one. The bottom will be calculated. So let's say I started with in this column 100 kilohertz, 100 kilo ohm. Output voltage is 1.0. This is the output of the divider. This is the input feedback voltage. Here is the output voltage of the converter, and you can see that for 100 kilo ohms upper resistor, the bottom resistor is 31 kilo ohms and 250 ohms. And here you can see that I can play with the numbers. If we choose 33, which is the standard value, and output is 0.1, so the output voltage will be 4.03, which is not enough. When we choose the 30, this will be even more. So yeah, nothing in between. So we have to collect our bottom part of the divider from 30 kilo ohms and 1 kilo ohm, or we can choose a different upper resistor. So when you can try some values, but it seems that all resistors should be combined with two or collected from two serial resistors, so it doesn't matter. So 100 kilo ohms plus 31 at the bottom is 4.22, which is quite good. So this is how you calculate the feedback divider. So we are here, and back to the implementation and application section. What interesting is here, bootstrap resistor, bootstrap capacitor. I think not 100, but 95% of all buck converters use 1 nanofarad capacitor for the bootstrapping feature or function. So this is the case of this regulator as well. So the bootstrap capacitor will be 100 nanofarads. I will save the table with all the values. So what else is in that table? There are bootstrap resistor, but in the schematic there is no boot resistor. I think we have to make sure what should be you can see here is the proposed solution. From the R boot there is a resistor to C boot. The recommendation is 0 ohm resistor, but in the simplified schematic there is a wire. I recommend to place the R boot resistor just for the sake of further testing, because this bootstrapping resistor can have significant value on EMI performance. And if you want to tune the buck converter for compliance with EMI standards, you need to work with this. The switch node is very sensitive, and everything which is involved in switching and the bootstrap capacitor and bootstrap circuit is definitely involved in switching. So I'm adding the R boot below the C boot. So R boot will be 0 ohm, like a placer. So what else is in the table? CVCC is always 1 microfarad. We have to choose, we have to verify what is the function of the VCC. Most probably it's the output of the internal regulator, but we have to check it. There is a section at the input when all features, all functions of all ports are explained. So VCC is the internal LDO output, exactly. Connect a high quality 1 microfarad capacitor from this pin to A, G, and D. Okay, so we are now sure that we definitely follow the datasheet recommendations and recommendations of the table 9-2. So CVCC, I'm adding it as well. So CVCC will be 1 microfarad up, high quality, they say. So it will be like, I think, ceramical capacitor X7R, X7S or something like this. So I'm making the note. Okay. What else? CFF and RFF. The values differs between the frequency setup and the output voltage. We have to choose and calculate our values. So now we are undecided about the values. So next, choosing the switching frequency, very important thing. This regulator works from 400 to 2.1 megahertz, but there are some limitations. Here is the formula number 1. Switching frequency must be lower or maximally equal to this. So I make some calculations. V out is 3.3. V in max, we said that the nominal input voltage will be 12. So we can use 12 as the input voltage max, and T on min is the parameter of the regulator. We have to check it in the data sheet. Yeah, here is the parameter. T on minimal or minimum is 70 nanosecond. 70 nanosecond is the maximum time that the regulator switch node is, or the high side switch is on. The on time of high side switch is minimal time is 70 nanoseconds or more. So we have to choose it in the equation, and when I place the numbers for 3.3 and 12 with 70 nanoseconds, it means that the switching frequency must be lower than 4 megahertz. It's okay because our maximum frequency of the converter is 2.1 megahertz. If we want to choose the input voltage as the maximum voltage of the buck converter, which is 36, so we would have 3.3 divided by 36 and divided by 70 nanoseconds. And the maximum frequency is 1.3 megahertz. Okay, so for the maximum input frequency, maximum input voltage, the maximum switching frequency is 1.3 megahertz. Okay, so we know parameter number 1, we have to go lower than 1.3 megahertz. And my recommendation is to go with 500 kilohertz, which is I think good number. So we will choose 100 kilohertz. Basically, we can choose anything between 400 kilohertz and 1.3 megahertz. I'm choosing 500 because I like that number. So, setting the output voltage, we already set and calculated the feedback resistor, so we are good to go here. Inductor selection. For the inductor selection, there is another calculation, very important formula for buck converters. We need switching frequency, we just set the 500 kilohertz. There is K, which is the percentage of inductor current ripple. Usually in all data sheets are value between 0.2 and 0.4. You can see that here for their example calculations, they recommend to use 0.25, which means that the maximal current ripple should be 25% of the nominal current set in the calculation, and the nominal current is not average current but the maximum current. Our maximum current is 4 amps for our device, but 4 amps will be our maximum current. Input voltage will be 12 like nominal, 3.3 will be output voltage, and this is everything we need. So when we use all these numbers, I got the number of, or the inductance of the inductor, 4.7 microhenry. But this is not everything we need about the inductor. We need to know the maximum or saturation current. As I said, the calculation of the inductance was done with the 25% higher inductor current than the average current is. So for 4 amps, we can go with 5 amps, but I think it's not correct. We have to choose the maximum current of the high side switch. So let's check the section 7.5, which is electrical characteristics of the buck converter of the component. And here we can see that the current limit, high side current switch limit is 8.1 amps. So this is the absolute maximum current of the switcher. There is node number 1. Let's check it. High side current limit is function of duty factor. High side current limit is highest at small duty factor and less at, of course, small duty factor means that we have big input voltage and small output voltage. It means that the switcher is switched, the high side switch is switched in a very short period, and much longer period is off. And when the voltages are almost similar, for instance, for 12 volt input, we will need, let's say, 11 volt at the output. So the switcher is almost always on because the output is very, very close to the input voltage. So the node is not important for us. What we need to get from this table is that the absolute maximum number, absolute current, maximum current is 8 amps. So our inductor will have 4.7 microhenry and the saturation current will be at least 8 amp. So what else? Let's get back to the implementation section. Inductor selection, we chose output capacitor selection. There are two tables, recommended values for ceramic capacitors only and combination of electrolytic and ceramic capacitors. We will go with ceramic capacitors only for the simplicity. And here are two frequencies as well. Transient performance is minimum and better transient. So for 2.1 megahertz, the recommendation is 2 capacitors of 47 microhenry. For 400 kilohertz, which is close to our number, there are 4 pieces of 22. So the total is basically, the total capacitance is basically the same, but they work with the probably the parasitic parameters like ESR or something. Unfortunately, there is no calculation, but I think we will go with the better transient. We will use 5 pieces of 22 microfarads. I believe there is a section that we have to calculate with the current ripple of the capacitors, but MLCCs usually don't have these numbers in the data sheets. So we will use the highest possible quality of the MLCCs, like X7R or something, in a big package, like 1206. So output capacitor will be 5 pieces of 22. So let's use it. C out will be 5, 22 microfarads. Our voltage, output voltage is 3.3. There is voltage rating of the ceramic capacitors. We don't need to use like 100 volt capacitors, but I have to check my library. I think 35 volt or 50 volt is something I will use. So let's say 35 plus volt, X7R or something, X7R. Okay, input capacitor selection. Okay, we need to choose this as well. They say that we have to work with the input current ripple as well. Simple mathematics say that our nominal input voltage is 12 and our output voltage is 3.3, which is about a quarter of the input voltage. When we want 4 amps at the output, there is some efficiency of the converter, but the voltage is 4 times higher at the input than at the output. So the input current will be, let's say, 1/3 of the output. So when we have 4 amps at the output, 1/3 is 1.33. Again, the MLCC's datasheet are not usually don't say anything about the input currents or maximum currents. So again, we will use the battery of multiple capacitors. Their recommendation is there is a minimum of 10 microfarad of ceramic capacitance. Yeah, I think we will use, I don't know, 2 capacitors of 22 of the same value as on the output to have the design lean. So input will be 2 times 22 microfarads, 35 volt plus. Here would be ideal 50 volts because the maximum input voltage is 36 and 35 volt capacitor wouldn't be enough. So I'm placing here 50 volt plus, X7R ideally. And when I spoke about the lean design, it means that even the output capacitor will be changed to 50 volt capacitors. So something like this. Bootstrap capacitor is 100 nanofarads and at least 10 volts. Okay, so I'm adding another node. 10 volts will be the minimum rating of the bootstrap capacitor of 100 nanofarad capacitor. and they are talking about the high quality X7R. Okay, X7R will be boot resistor. We already found that it will be 0 ohm placer. VCC will be 1 microfarad 16 volts. Okay, I am adding the note about 16 volts. The bias. The bias here is the, what is here in the schematic? Yeah, the bias is the, like the net from output of the converter. Let's check the paragraph of the bias. Yeah. Okay, to prevent V out noise and transient from coupling to bias, a series resistor 1 ohm to 10 ohm can be added between V out and bias. Okay, so another point. So bias input we will use 10 ohm resistor from V out to bias. Okay. What else? CFF and RFF selection. Yes, these are the feedback compensation resistors. Let me show you. Here are the RFF and CFF components. We are talking about these two components. So, I'm sorry. So let's get back to the proper section. And they say the feed-forward capacitor is used to improve phase margin. And transient response, since this capacitor can conduct noise from the output of the circuit directly to the FB node, a 1 kilohertz resistor, kilo ohm resistor can be placed in series with CFF. If the ESR0 of the output capacitor is below 200 kilohertz, no FS must be used. Okay, so basically there is no calculation, no formula, but I will use the values from the table, just the component placers, and then we can choose. So let's say we have very close frequency frequency to 400 kilohertz, so we will use these values. CFF will be 4.7 picofarad, 4 pico 7, and RFF will be 1 kilo ohm. 1 kilo ohm. Okay. So what else we are missing? Our table is filled. Let's continue with the data sheet. What else is there? There is the external under voltage lockout. In the reference schematic, there is no divider at the enable input. There is only the pull-up resistor to the input voltage. So we can place the full divider, but we don't need to place the bottom resistor of the divider. So yeah, I think it's nothing against anything. So here is the calculation, and the bottom resistor is chosen in the range of 10 kilo ohms to 100 kilo ohms. So for this, we need to know the input voltage of the under voltage lockout circuit. So we have to check the data sheet. Section 9, do not float. Section 9 is our section, so we are going in the circle. So here is the pardon. Here is the section of the cannot be floating, but I can't see the input voltage. Once the N voltage is above Vn, okay, Vn wake is 0.4 volt. So it means that when they are talking about 100 kilohertz for the bottom one, and the input voltage of the enable circuit is 0.4, there will be some mega ohms at the input. The simplest way to enable is to connect to Win, allowing soft start. Okay. Okay, I will use 1 mega ohm for top, and I will not use the bottom one, and the unpopulated resistor will be 10 kilo ohms. So I am going to add 2 more points. So R enable upper will be 1 mega ohm. The R enable bottom will be NC 10 kilo ohms. And I can see we have some comment. Hello, Fernando. Oh, thank you for the question, Fernando. I can recommend going to 𝗏𝗏𝗀𝗃𝗀, which is platform with the best courses on the internet. 𝗏𝗏𝗀𝗃𝗀. Yeah, here is even my course, but I don't recommend you my course because you are experienced designer, and you can search for advanced. There is multiple advanced courses, but I don't know why the search don't work. So advanced PCB layout course by Robert Feranec, very recommended course. This one as well. There are courses by Philip Salmoni. This advanced digital design is very recommended and very popular. This is my course, but as I said, this is not for you. So basically, you didn't mention what EDA tool you use. If you use Altium Designer, you definitely want to go with the Robert's courses. If you use KiCad, I don't know what EDA tools are used in this course. Yeah, it's EDA tool agnostic. Okay. So yeah, it's up to you. Choose from these courses and you will not go wrong. So let's get back to our buck converter, and I think we are good to go. So we have all values we need, and the implementation section, there is only syncing of the converter when there are more than one converter. Nothing what we should need. Power good is there will be like 10 kilo ohms resistor, nothing important, just a test point from the power good output. Okay, this is what we want to know. So let's create the schematic. So the description will be LM 61440 eval board. So this, nice. I think I will set the page format to A3 because our test description already takes quite big area. there is a comment by LinkedIn user. SOC design is very different than PCB design. Okay, so I think we can get over this comment. And Fernando, feel free to chat with the LinkedIn user. I don't know if you want or not. So I am using this symbol. Okay, and you know what? I will keep the split screen because there is the reference schematic and it will help me. So as I said, there are two power entries to the switcher, and we said that we need to use two 22 microfarads 50 volts plus high quality capacitor at the input. So this will be input, and at each power entry point there will be one capacitor. I say 22 microfarads 50 volts or more. I don't have in my database such capacitor, so I can check the 10 microfarads. This is electrolytic. I don't like it. Here is, I think, our capacitor, so we can choose two of these at each side. So yeah, the component placement will be a little bit more difficult, slightly more difficult, because more components means more work, but I think it's no problem for us. So here is our capacitor pair. So we need ground. So this is our battery on the V input 2, and this is for V input 1. So here will be our 12 volts input. Yeah, basically it will be VCC, but the nominal voltage of our converter is 12 volts, so you can use this. Power ground is where the capacitors are connected. So for the simplicity, I will place just this ground symbol. We say power good. Power good is the output pin. So I will place the 10 kilo ohm resistor here, and the output will be 3.3. It will be our future output. I already placed here the power symbol because we know that this will be our output. Yeah, we said that the input upper resistor will be 1 mega ohm and the bottom one will be not placed 10 kilo ohms. So let's place 1 mega ohm to the input. Yeah, I'm looking at the clock. It's 50 minutes. We are 50 minutes into the stream, so I think I will finish the schematic and we will continue next time with the component layout and the PCB layout. So this will go to the ground as well. And as we said, not populated. Oh, that was too fast. This one, RT resistor, it needs to be set. This is my fault. RT resistor, there should be some calculation or graphical representation of what resistor is for what switching frequency. Yeah, we have the comment. Yeah, for sure, 𝗲𝗁. This time I want to go through the data sheet, because the disadvantage of the webbench is that people who are inexperienced with the circuit design can't see the equations and formulas behind. So of course, everyone, you can choose the webbench, but you have to follow the values the webbench will give you. If you start with the datasheet and your own calculations, you will get your values, and then you can compare the values with the webbench Power Designer. Yeah, and if you are asking me, would I recommend? Yes, I would, but as a second step. The first step should be going through the datasheet, checking formulas, going at least rough calculations, and then verify your calculations with the Power Designer, with the webbench. The thing is that sometimes even the webbench or similar designers can be wrong, and you don't want to be wrong. So use it as a checker for your calculations. Thank you for a great comment. I'm looking for the RT resistor value for the 5 kHz switching frequency, and I'm happy. Here is the value in some example circuit, but still I want to know what is the calculations. So let's check the data sheet, the port section, RT. Yeah, here is the range of the resistors, but still I want to know the exact value. So switching, let's look for switching frequency, switching. Here is the calculation. Here is the formula. So there will something like 26 kHz or similar. Yeah, definitely it's better, but there is an issue. You need models of the components, and not every manufacturer will give you the let's say open models. Texas Instruments will give you some encrypted SPICE models, but you can't use the encrypted SPICE models in LT-SPICE. So if you want to simulate the circuit with LT-SPICE, you have to choose components which have models compatible with LT-SPICE. So yeah, either you have to choose the, let's say, analog devices or former linear technology. Usually all their models will be compatible with LT-SPICE, or you can choose from majority of reliable manufacturers, but you don't have the SPICE models. So yeah, you have to balance this. So let's back to the calculations of the switching resistors. So our switching frequency will be 500. So 1 divided by 500 kHz minus 3.3 yeah, so probably it's switching frequency minus 3.3, and this is below the 1. So 500 kilohertz minus 3.3. It doesn't make sense. Yeah, I'm getting the negative voltage, negative number. The switching frequency gives me 2 times 10 to minus 6, and when I make the calculations with minus 3.3 times 10 to minus 5, I will give negative number. This doesn't work. So this is something that probably the 𝗲𝗀𝗃 will give you. You can choose later, but I think I will give the number from the picture. So we have 500 just in between these two lines, and there is something like 26. So the value from the example circuit will be was correct. So I'm going to check this here. 26.7 is probably the good number. 26.7 kilohertz. Okay, so we will see. Another comment. Yeah, so build on your small practice. Choose low expensive components, visit the distributor website, for instance, 𝗏𝗁𝗃 or DigiKey. Look for, if you are talking about the buck converters, look for buck converter. Let the output sort by price, and you will get your converter for, I don't know, 10 US cents. Then you have some capacitors, inductor, and I don't know, for $2 you have the entire circuit. You can use your breadboard or just wires. If you want to design a PCB, you can choose manufacturers like JLC PCB, and for, I don't know, there is some initial price of $2 per PCB, and there is some shipment. So yeah, the PCB will be much more expensive than the components, but yeah, it's an disadvantage of the hardware design. You need to have some money, but I think you can go with very little money. Yeah, as I said, start today. There is no obstacle but the money. But yeah, if you drink coffee and you buy coffee, so don't buy coffee, buy your components. That's my advantage. Advice. I'm sorry. So 26.7. This is not the very standard value. We can use 22 kilo ohms plus 4 kilo 3. This will be 26.3. Quite good value. VCC will be 1 microfarad to the ground. 1 microfarad with 16 volts at least. So 1 micro, 16 volts, we say X7R, this one. This will be ground. So we say 22K plus 4K3 Yeah, I will rearrange the top resistor to be above the bottom one, like this, just for the sake of the schematic, like pureness or clarity. So feedback resistor switching bias. Okay, we have to work. Bias will be 10 ohm from V out to bias. Okay, so will be 10 ohm resistor. As I remember, it will be for the EMI or something like this. So this will be output. Here is the switch node. We say 4.7 microhenries, and I say the maximum current will be 8 amp. I have to check this one. This one looks good because there is a note about 8 amps saturation current. So let's check this table. 4.7 current saturation is 10 amp. It's fine. This is our inductor. This is our inductor. Output capacitor, we set that output capacitor will be 5 pieces of 22, quite a lot. So 22. And because I didn't use 22 at the input, I can choose anything like smaller output voltage. This is 1210, like big package. This one is my favorite, but it's not in the high quality material. So let me check this one for the material. There is no note in the data sheet, so no, in the item, in the attributes, so I have to check it. This is this one, and this is very low quality material. I will definitely not use this one. So this was the material. No. Epsilon 5V, and the data sheet is here. So okay, I will use this one, X7R. Why not? Five of them, so I have to make some room for each one, like this. Yeah, I want to have all the ground symbols in the line. again for the sake of clarity and elegance of the schematic. This is the bias input. Okay, what else? What else? Feedback register boot. Yes, boot. We said that boot input will have 0 ohm placer. 0 ohm placer for 0.0603. This will be our register, and the C boot will be 100 nanofarads, at least 10 volts. We will use this one, high quality X7R material. This, and finally feedback resistor. I will use something like this. It's not something super beauty, but doesn't matter. And the bottom feedback resistor was calculated as 43K. Although it was not calculated, it was taken from the table, but the result is the same. And if I remember correctly, there was a series combination of C and R for the feedback compensation, and the FF capacitor and resistor was 4.7 pico and 1K. So 4 pico 7. Oh, I was okay. I don't want to. You know what? I have to. It's not correct to use different size of the capacitor. So I have to use 4.7. There is only 2.2 in my database, so I will save a copy. COG will be okay. We can use Mauser, GLC-PCB as well. 4.7. Okay, so let's check Mauser. So we have 4.7 capacitor. Oh, I made a mistake. 4.7 pico, 0.3 COG. So something not super expensive, Murata, or yeah, maybe X. Yeah, this looks good. This one. 24. This one is better, 50 volts. This one, I will use this one. So here is the manufacturer order code. Here is the data sheet. And I have to find GLC-PCB code. This is our code. Okay, so let's fill the attributes of the symbol, manufacturer's order code, and the GLC-PCB code. Now we are good. So 4.7, I have to change the value. I don't need the material in here. Okay, update the symbol, 𝗶𝗶, and 1K. Beautiful. So what else is in the data sheet? Yeah, we are done. We are done. This is our output, 3.3, and we have to add some test points. Test points. I think the circle of 2 millimeters will be fine. So at least here. This is E out. We will use one here. This is 𝗶𝗶. Yeah, we have to check the undervoltage lockout, the enable input, so we will need a test point. I think we are good. Okay, so here is our schematic. I can go with this schematic as an entry point to the live stream next week. So I hope you enjoyed the stream today. We went through the circuit design and schematic design of the buck converter based on LMR 61440, which is low EMI, 36 volts input, 4 amp output, synchronous buck converter. So thank you for watching, and next time we will design the PCB for it. So see you. I'm going to check the comments. Yeah, thank you for that question. That question is good. If I understand correctly, you want to only check the value, change the value from, in my case, 2.2 pico to 4 pico 7. So you just wanted to change the value. Okay, but see what is in my symbol. There is data sheet, no problem. There is the description, you should change the description, and there is a manufacturer order code. This is why I am doing it, for the manufacturer's order code. Why? Because at the end of the design, I will export the bill of material, and I need part numbers, which means a manufacturer's order code. When I change only the value, there will be a mess, or there will be no manufacturer's order code. And do you know when, at which stage I do most mistakes in my entire life? Component sourcing. When I don't have the correct part numbers, I definitely buy wrong components. There is no way. There's a way to hell. So if you don't want to get to hell, please use correct, valid, and verified part numbers. Please do. So thank you for the question. That was a good question because, yeah, I think if you want to get anything from this session, take this. Use correct part numbers. See you next time.